Hello and welcome to episode 2 of Q for Problems. Today we'll be looking at problem 2 from the Project Euler problem set, which wants us to find the sum of the even terms from the Fibonacci sequence whose values do not exceed 4 million. So the Fibonacci sequence is a sequence of numbers whose values are found by adding the previous two terms, starting at either 0 and 1 or 1 and 2. So in this example shown in the problem, starting at 1 and 2, the third term is 3 and it's found by adding 1 and 2. The fourth term is 5, found by adding 2 and 3. So jumping into our developer, so if we start at 0 and 1, we can say show x equals sum of minus 2 take x. So minus 2 take will essentially take the last two elements of x, we'll sum them and join it on to x. So if I run this, you can see it gives us 0, 1, 1, run it again, the next term 2, run it again, the next term 3. So turning that into a function, you can just do x join sum minus 2 take x. So if I do f on 0, 1, 0, 1, and then if I do f on that, and then do f on the result of that again, you can see it gives us that. However, rather than having to apply this many times like this, we can use a do construct. So the do keyword is, it's not a function, it's actually a control construct. Its first argument is the number of times you want to do something. So we essentially give it 10 here, so we'll do the first 10 numbers of Fibonacci sequence. It'll actually be, the first 12, but because we're starting at 0 and 1, they'll be included as well. So every now arguments in the do construct is will be ran this number of times. So we want to just do x assigned to f on x, and then we will print the final result. So if I start x at 0 and 1 again, and then run this, you can see this is the first 12 Fibonacci numbers, 10 plus the starting point. However, the do construct is not seen as good practice in Q. It's better to actually use the over iterator or accumulator. So that is either the over keyword or the /. So how do we actually use this? Well, the syntax is very simple. So we'll give it our 10 again to do this 10 times, and then our function with the over accumulator. So this essentially turns this to do this f, apply f 10 times to its right argument. So we're going to start on 0 and 1. And you can see it gives us the same result as we had before. So to actually see what's going on here, you can use the scan. So the over will just produce the final result, but the scan will actually show you intermediate results. So that's the \, but the same syntax. So you can see if I run that, you can see each step. So what it does is it starts with this, is what we give it, passes it to f, produces the result, then does the same again, passes this to f, produces the result, passes this to f, etc. And we'll do that 10 times. So this is called infix notation, where the left argument is on the left and the right argument's on the right. We can also use bracket notation, because we are going to use the bracket notation for simplicity in our function. So the first argument here is 10, and starting is 0 and 1. So this will do the same job as the infix, or changes to a / and see the same result. So that actually gives us now the basis to create our Fibonacci function. So we just want to take the f we had before, and then we're not going to give it any first argument because we don't know how many times we have to do this. So we're not going to give it any first argument, and then we'll start it at 0 and 1. So that's our fib function. So now if I was to run fib 10. This will give us the first 10 Fibonacci numbers plus the first 2. So we only want the Fibonacci sequence up until the values that do not exceed 4 million. So instead of using the do construct here, we can actually use the while construct. So the while, it's the while overload of the over accumulator. So how do we do that? Well, the do is decided by giving this an integer value, i.e. the number of times you want to do this. However, we can, instead of giving it an integer value, we can give it a predicate function. So that is a function that will return a true or false value based on some test. So the predicate will receive the output of this and evaluate it, and if it's true, it will continue to go, and when it's false, it will stop. So build our predicate function. It will simply just be this and 4 million. 1, 2, 3. So what is this firstly? So this is actually a projection waiting on one argument. So the first argument is given as 4 million. So that will be this x, and the second argument is the output of this at each step. So as you see here before, the first time it receives this, or the first output will be this. So it will receive this, then it will receive this, and it will receive this as its y argument. And you can see we're doing the last on it, so each time it will be 1, 2, 3, 5, 8, 13, i.e. the last item each time. And as soon as it finds one that exceeds 4 million, this will now produce a false value, which means that this will stop. So if we actually pass that to fib, so if I run fib on this fib, you can see it gives me up until, so it gives me the first value that does exceed 4 million. We can get rid of that by just doing a -1 drop. So this just removes the very last item. So if I run this again, you'll see no, it's the same list, just with this item removed. So that's all the Fibonacci numbers that do not exceed 4 million. So we can, instead of giving this a fixed argument of 4 million, we can turn it into a composition function. So fib m, we'll call it, for fib maximum, up to a maximum. So the reason we have the ampersand here is to turn this into a composition. If you didn't have this, then it would think, the fib would try to evaluate straight away with this. However, this tells Q that this function is waiting on another argument. So you see, if I run this without it, you can see I get a type error. But if I put the ampersand in, the at symbol, continuously calling it the ampersand, the at symbol, it will actually create this composition function waiting for an argument. So if I run that and define it, and then I run fib m on 4 million, you can see now it's given me a list. So now that's all left to do is to just filter this list just to have the even numbers. So the best way to check if something is even is to do the modulus with 2. So if it returns 1, then it's an odd number, and if it returns 0, i.e. remainder 0, that means it's evenly divisible by 2, which means it's even. So we can actually create a function here is odd, because it will give me 1 for the odd numbers, i.e. a true value, and it will give me 0, i.e. false, for the even numbers. And then from that we can actually build a evens filter. So if I just give this 1, 2, 3, 4, 5, just so we can see the output. So essentially, if I do is odd on x, you can see it's actually giving me a 1 in the odd places and 0 in the even. So if I actually just check where those zeros are, 0 equals, then you can see now I've got true values where there's an even number and false values where there's an odd number. Using the where keyword, we can find the indices of the evens and then actually index into the original list. And there you have it. We have the even numbers. So we can call this function evens and then apply this to our evens fib m of 4 million. you can see this is the even Fibonacci numbers do not exceed 4 million. So all I need to do is sum the result, and there you have it. Looking at the performance, then you can see here that this is the final result. This is the solution. So we've used the at to create a composition again because if I didn't have this at, then evens would try to evaluate with the argument of this function. However, this tells it that fib m is waiting on an argument still. So that's yes. And then if I was to do this in full form, rather than doing this as many functions, which makes it a lot clearer, and they do it in the full form, this is how the solution would look. And just to run then 100,000 times each, just to see the performance. So you can see the actual full form has very slightly worse memory usage, but it's but the timings are very similar. But yeah, please post your solutions, and yeah, thanks for watching.